Okay, hello. My name is Jimothy, and I'm in a cafe right now, so I apologize if there's a bit of external noise coming in. But today we are going to look at internal forces. This is often overlooked, and really why we're going to look at it is because we have a lot of problems where, let's say, we have some cylinder here and some force applied here, and we want to find the stress and strain on this surface right up here. And this is a very common problem. You can use it to find areas of stress in bones, in metal beams, in a whole bunch of applications that are very important for lots of engineering and biomechanical tests and making products so that they work. But in order to solve these questions, we need to understand three things. First, we need to understand internal forces. Second, we need to understand NT coordinate systems. And then third, we need to understand how to project vectors onto different axes. And in this video, we're going to just focus on this top one because I find in a lot of biomechanics classes, it is overlooked and kind of just expected for you to intuit it, which sometimes it is not as easy to understand. So first, when we're looking at this stuff, we can shrink this down here. So when looking at internal forces, we understand that F equals mass times acceleration, right? And so we know that if we have an object and we apply a force on it, and this object has a mass, it is going to end up accelerating in that direction or in a direction, right? We also understand that we have something when we have the sum of forces. If we assume that the sum of forces equals zero, that that means the mass times acceleration equals zero. And if it has mass, that means that A equals zero and it is not moving, right? So, for example, if we're looking at the arm, that's your elbow, and we know we have two bones here. We're just going to group them as one, right? And we know we have some force here. Maybe someone's also grabbing on the arm and pulling it down here. We call that F1 and F2, right? But if we assume static equilibrium, we assume sum of forces equals zero. So we assume, making that assume sum of forces equals zero, we then assume that the forearm is not moving, right? So we assume that this is not moving because the guy's elbow isn't getting dislocated and he's flexing his muscles, which is holding the arm still. So if we look at the system, if we define the system as that forearm, and we have these two forces on it, if it was only these two forces, that would probably cause the arm to move this way, right? Like if that arm was floating in space and we applied F1 and F2, it's going to move somewhere in that direction. But we know it is touching this joint over here, so we know that since the sum of forces equals zero, that F1 plus F2 does not equal zero. So that means we know that there has to be some other force acting on it, and we can just assume some force Fx and some force Fy. Because then we add Fx plus Fy, then this could equal 0, and we could solve for these values, right? And these joints are going to come, or these forces are going to come here, are again coming from reaction of that elbow. But that's because we defined this system as the full bone. What if, what if we cut the bone in half and we just wanted to look at this part of the bone? Well, just looking at that part of the bone, we'll redraw that end piece. We know with these forces that the guy's arm is not breaking, so we know that this part isn't moving down. These forces are not pushing it, or else his arm would be broken, right? So if we just look at this area, same thing. These forces are going to want to move it there, meaning there has to be some sort of force to stop it. And that force is an internal force. So that means there's a force happening inside the bones that are going to be some some X force, some X force, and some Y force are happening inside the bone to stop it from breaking or failing and holding it still. So the internal forces, the forces inside the bone, and we can cut the bone anywhere. Like if we were to here in the when we had the full bone, we have those elbow forces, but we could even cut the bone right right in the middle, right there. Oh, stop there, bang. And again, same thing. There's going to be some forces happening inside. As long as the bone's not breaking, and as long as we assume static equilibrium, there's forces inside resisting it from shooting off this way, right? If we didn't have static equilibrium, then yes, that could happen. But we know the bone is not breaking, so we know there is internal forces. So this allows us to then be able to look inside a bone. Let's draw an easier one like a femur. That's an okay femur. It's thick, but this allows us to, we have a force acting on the femoral head, right? We can take peeks and look and see how the forces and moments are at each point in the bone, and we can identify areas where it might be weaker, right? So this is hugely useful for understanding fractures, why things fracture, and also how to reduce that risk, and also in surgical planning to understand where you're putting things in order to best help that case. So this is hugely helpful and a very important topic, because when we are able to look at these sections, we can then calculate the stress and strain of that area, and that again gives us lots of information, which is hugely important. Okay, that is all for today. I will be going over NT coordinate systems in the next video, a continuation of this one. Thank you. If you have any questions, let me know. Have a good one. Okay, so we understand internal forces. They make sure that the bone does not break and hold it in place. It's like we said, part of the bone doesn't fly off, right? In this case, this bone doesn't break. Why doesn't it break? Because we have internal forces here. We actually have internal forces at every single slice, but we're just able to calculate them at one slice at a time in this course. You then can find equations for how those internal forces change throughout, but we don't need to do that. We just need to be able to look at certain areas and calculate them. So the next thing we need to know to do these problems for stress and strain on these slurp surfaces is NT coordinate systems. So an NT coordinate system stands for a normal and tangential coordinate system. Normal, if we just give a definition, is used in linear algebra a lot as perpendicular, which we know is when something is 90 degrees to another. So we had a surface here, perpendicular, or the normal vector would be this way, or just a line that is 90 degrees perpendicular. Tangential means, well, tangent. And if we remember from math and calculus, if you took any, tangent is if we have a curve like this, it's the line that touches but does not cross. So here, this crosses the circle twice. This just touches it. And if we look at the normal to that line is here. So this is a coordinate system. Why? Because they're always 90 degrees apart. But if we look, you're like, well, I don't see any curves. We're normally given flat surfaces. What are we doing? We can think of tangential as parallel to the surface. So, for example, if we are given a surface like this, and we want to define the NT coordinate system, we are going to have normal here and our tangential as here, right? This is completely kind of parallel to that line, and that's normal. You really just have to understand one of them. If you understand normal is always perpendicular, you know tangential is just 90 degrees. And so that's always going to end up on that surface. So this is N, and this is T. So for these next systems, give it a go and try drawing the NT coordinate system just like we have up here on here. Don't worry about the direction of the tangent, but give it a go drawing those. So that first one, we know that surface is there, so this is going to be our N. And in this class, we do not really care about direction, so we are going to have T tangent there. This next one, same thing. It's almost like a mirror image. We have N up here, and we have T right here. And lastly, we have normal N here, and we have T right here. So this is the same thing as our coordinate system, but it just kind of tells us it is normal and tangential to some surface. It's used a lot in physics when you're traveling on a curve because you're going to have that normal acceleration and tangential acceleration, as well as tangential or just the velocity. But here it helps us understand stresses, strains relative to the bone, right? Because if we just followed x and y, right? X and y, that's different. If we calculate something here, that's different relative to this long axis of the bone. And then here, that again is different than here. Like, for example, if we wanted to find like that normal vector is always perpendicular. In these cases, it's always in line with that body of the bone, right? Whereas if we use this is in line, this is not in line with that body of the bone, that long axis, as well as this. So having these NT coordinate systems allows us to standardize our coordinate system to the object we're looking at so we can compare between bones. Because if we just used X and Y, then depending on the orientation of the bone, we're going to get different answers. Whereas if we did NT, no matter what, we know that orientation is going to be the same relative to the bone. So that's why they're important. And I hopefully that last point kind of stuck on why we needed them, because it allows us to compare between bones because we're having the same reference point. Now, one thing I want to go through, the last thing we have is projections. But before I go into projections, I just realized I needed to add in some NT examples where they are not completely flat across. So let's say in this example, oh no, this example, we don't want this surface, we want an angled surface, right? We cut the bone this way, and we can have a straight line there. We want to look at the stress that compresses it one way. How do we draw our NT coordinate system? Well, the same way. We identify that surface that we're looking at, and then perpendicular. So there we go, just like that. And that should be a little 90 degrees. And then we have our tangent, our T, NT. And if this bone was rotated like this, same thing, right? You want to find perpendicular to that surface, 90 degrees, and then tangent, kind of in line. So there you go. Now projections, right? We'll clean that up a bit. So projections, right? Out of the three, we understand internal forces. We now know normal, tangential, NT coordinate systems. And the last thing we kind of need is, I would say, probably the most important one, the easiest to mess up, is projecting vectors. So, where are we going to project the vectors? We do it all the time, but in just a new coordinate system. So, projections. We know when we have x, y coordinate systems, if we have a force vector anywhere, right? Maybe I draw it over here. We have some force vector here, right? We can bring over a coordinate system and decompose this vector into an x component, fx, and a y component. Okay, interesting. Right, and we know that then f equals fx, we can write it this way, fy, or we have our nice notation of fx times I plus, in this case it's a plus, fy times j hat. And this, again, just means it's this axis. So it's basically a number projected in the direction of x plus this number in the direction of y. And we remember that our vector addition, right, tip to tail, we add two vectors, tip to tail, then we get our actual vector. So we know all this. We understand this, and we understand that in this case, we bring that over here to find fy and fx, right? If we're given an angle here, theta, that we know that fx is going to be magnitude of force times cos theta, because that's the adjacent side. And in this case, Fy is going to be same thing, but sine theta, because that is the opposite side. And if we're given if we're given the angle if we're given the angle up here, right, these flip, where we now have fx is sine, right, because this is the angle, and now the blue is on the opposite side, so fx is sine, and fy is cos, because this is the adjacent side. So either way, we can decompose, and we're projecting this vector onto the y-axis, and then we're projecting it onto the x-axis. What you've been doing is projections. In this case, we are going to do the same thing, but with an nt coordinate system. So we have our t, we have our n, and again, it is the exact same thing, right? Here we have our vector. We just need to find an angle here or an angle here, one of the others, and that will allow us to find the adjacent edge and the opposite edge, and that makes our right triangle. So everything is triangles, and this is just now we're projecting, rather than projecting onto the x, we're projecting onto the t, and then the y onto the n. So they're the same things, and if we look at it down here, right, and we move it back, in this case, if we had our angle here, we know this side is adjacent, cos, and this side is sa, so opposite, so we use sine. But the one thing we do have now is it would be ft and fn, because this is in the same direction here, and this is the same direction there. You can think about it. I draw it in triangle because we're recognized to it, but yes, technically we're projecting here and projecting down here. There's many ways to visualize it, but it is the exact same thing. How to do it is basically we know how to do once we get to this step, we understand what to do. Hopefully you do. If not, you can review some trigonometry and your forces, but we should know how to get them, use these equations to get this direction and this direction. The main issue is finding theta. And I'm going to show the method that I find really simplifies things and will help you find that angle no matter what. But that is a bit of a review of projections. So we technically now, we know all three, so we can now solve. Sorry about that, got interrupted there, but yeah, so this last part, like I said, we understand projections. We do it in the x and y, and we can do it in a new coordinate system in nt as well. So it's the same rules. That main part is finding that angle, which some people find hard. So here are two examples in this question where it asks you to, one, draw the coordinate system, and the two surfaces which we see are here and here. We are then asked to calculate the normal or axial force acting through the bone in each of those cases, and we're given F1 and we're given F2. So I'm going to kind of walk through more than what this question is asking, just to kind of complement the video and get an understanding for what we're actually doing. So in this case, we see that we have a force acting on this bow. And if we define our system as that blue highlighter, we know if we assume static equilibrium, in that case, we know that it is not moving. That this force, this force normally would cause this bone or this portion of the bone to move. But we're assuming that this bone is not breaking and not moving. Therefore, we know that there has to be some reaction force on the other side to stop it. Because we know that F1, which equals 550, does not equal 0. So we know that it has to be something like F1 plus F, we can call it I for internal force, which gives us 0 to show that it's not moving. So that first step is now that we know there is a force, is finding a coordinate system to represent that force here. And that's where that NT coordinate system is. So if I draw a rectangle to represent it, I will draw that rectangle up here. We have our force acting down here, and we know it is at 70 degrees from that axis, and we can draw our coordinate system here, where that is our normal, and then we can draw our tangential here. We're only focused on normal for this question, but there we go. What other information? We know that this is now 30 degrees. And what do we find? We want to find the normal or axial force acting through the bone. So we know that this force can be broken down into a tangent component we can call Fp, as well as a normal component we can call Fn. And we want to find this Fn because that'll then tell us what the reacting Fn is, because we know that Fn plus Fn equals 0 because this bone is again not moving, and we assume static equilibrium. So how do we find Fn? Well, I like to say as align the angles. So we know we can take what these two angles have in common is they are both in reference to roughly that x-axis. So we can then take this, drag him down, and put him, we can actually drag them both over. Or even better yet, we will just duplicate, bring it down, and here we will duplicate and bring it down. Right? And so just cleaning that up down here, getting rid of the highlighter, we see we have 70 and 30. We also know if we extend this, we know that this side is 30. And so we know, just through basic trigonometry, that this side is also 30. You can look and do the calculation yourself, but it is true. Same thing that if we continue this side, we know that's like 70. So what do we want in a projection? We want the angle between those, right? We want the angle between the force and that normal side. So I'll write that down. We want to find the F or normal component. We need to find an angle between the normal and the force vector. So here we can do that because we know that this full angle is 70 degrees and that this small angle is 30. So that allows us to calculate this angle, which is going to be 70 minus 70 is the full thing, minus this portion right here, which leaves us this portion. So 70 minus 30, which is going to give us 40 degrees. So we now know we can draw this here where we have this force and we have the normal and we have our right triangle where this is 40 degrees. Therefore, we know to find that blue, just like we do for x and y, is we do f, magnitude of f, times cos 40. Because again, this is on the adjacent side, which is going to equal 550 times cos 40, which gives us, if we look, 550 times cos 40, which gives us 421 newtons. 421 newtons in that n direction. So this will allow us in a future step to calculate normal stress because we want that force in the normal direction. We want to see how much it's getting squished per se. Okay, now I will copy this one over to the next page. And again, if you didn't do that first one, I highly recommend you give this a pause. You can then our rectangle, which represents we can draw a rectangle, which we can represent here. We know our NT, that's our N. We're only focused with the normal component right now, and we know we have our force. We have our force at, again, 15 degrees F2. We'll make this black again, just for ease. And so we want to find the N component of this force. We want to find this N component of this force, and that green is representing the tangent. So how do we do this? We again need angle between N and F, right? And so how can we do that? Well, we know that F, if we take him here, we know this guy will extend him a bit. And we know this is 15 degrees. And we know if we draw this N up here, we know that this is also from that x-axis. That's 15 degrees. And then we know that this is 65 degrees. So we want to find this green angle. We know that this green angle is 65 degrees minus, we want to take away this 15 down here, so it is minus 15 degrees, which gives us a nice 65 minus 15. You can always use a calculator if you don't want to make mistakes, which gives us nice 50 degrees. Now, okay, sorry, got cut off. Yeah, so we have 50 degrees, and then we can then redraw our triangle that we know now, where we have that force, oh, it's a mini guy, and that normal direction, right? And again, we want to project onto it, and we know we make that right triangle right here, where this is technically FT, and if we draw little FN. Oh, so we can now solve for this because we know that this angle is 50 degrees. And this, of course, is magnitude of f. So we know that Fn, if this is a triangle, right? We have this triangle where this is a 90 degrees and this is h. We know we can get that adjacent side by then by Fn equals magnitude, or that hypotenuse, times cos 50, right? Because we want that adjacent side right here. If we were given another angle on the other side, we could use sine, but in this case, we are not. So we have that Fn equals, value is 3,300 newtons times cos 50. And putting that into the calculator, 3,300 times cos 50 gives us 21.2 equals 2,121.2 newtons. And that is in the normal direction. So I guess this is the magnitude of the normal direction, right? And why is it important to know this force? I guess I could have talked about this earlier, but if we want to know, we have a bone and we want to know only the compressive force that squishes this. Well, no matter what force we have, we can then, if we have a force here, that's again broken down into the tangent and normal. But this tangent, this green one, applies a force here, does not compress this. It is only these blue forces that work to squish this bone. These ones are going to shear and like maybe twist, for lack of a better word, but we'll get into what that actually is later. But we want to look at the things that squish it, because that can cause certain types of fractures and breaks and damage and micro damage. And we will learn about different ways that bone adapts to these damages and why it's stronger in that direction. So finding and being able to find the component of the force that's normal helps us look at a whole bunch of things. So that's why we need it and why it is so important. So thank you. Thank you for watching. If you have any questions, leave a comment or message me. But yeah, hopefully that makes more sense and helps a bit for trying to find angles. Because the way you find an angle is you basically align them. Like this case, right, we had that force here, and well, we had the force here, and then we have that angle here, right? And we just take it and align them, and then that just makes it so much easier. So aligning those vectors and just taking the force and just putting it to something you know is going to help you, because you can. It's the same direction here as it is here. Same thing. Northwest is pointing roughly northwest. Down here, still pointing roughly northwest. So that's the easiest tip in my mind of doing it, is you just drag it and place it here. Right? Worked in the previous one. You just took it from here and drag it down to the bottom. Looks a bit scary in that one, but hopefully this one makes sense. Thank you.